Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have shown how we can calculate the settlement of a dry sand layer, all layers under earthquake shaking. Now, today's lecture, the topic is the seismic or liquefaction hazard mitigation. So, before I go to that topic, I will first finish the settlement of sand part, because I have discussed only the dry sand part. Now, today I will first discuss about the saturated sand part, then I will go to the liquefaction hazard mitigation part. Now, the saturated sand, the similar type of technique we will use for the saturated sand. So, let us discuss that one. So, I am taking the similar type of layer, okay. So, it can be a same as a sandy layer with different N value. Either you have different sand layer with different N value, or if you have the same sand layer with different N value, and based on that, even that sand layer we can divide it into number of sub layer. So, here it is also 4 sub layer or layers, it is been divided. Okay, so here also we have taken the thickness of that layer or depth of the layer, or I should say thickness the same as 8 meter, and the layers sub layer thickness are 2 meter each. Okay, and here the water table is at the ground surface. Okay. Now, remember that water table can be below the ground surface. In that case, this procedure is valid for the only saturated portion. Dry portion above the water table part, you have to follow the previous procedure. Clear? This procedure is only below the water table or saturated part. Dry part or above the water table, you have to consider the previous procedure that I have discussed. This procedure is also proposed by Tokimatsu and Seed 1987. So, here N160 is different for different sublayer. It is 6, here it is 10, here it is 8, here it is 12. Okay, so based on that, this is the average N value over this depth 2 meter. This is the averaged N value over the depth of 2 meter, you can say. Okay. So, this is a loose sand, previous one was also loose sand. So, here I am also designing it for MW equal to 8 with Max by G is equal to 0.25, and gamma sat here you will use, and that is 90 kilonewton per meter cube. So, my gamma sub, this will be 19 minus 10, that is 9 kilonewton per meter cube, provided we have considered gamma W as 10 kilonewton per meter cube. Okay. So, here suppose again we are making one table. So, this is my say layer 1 or layer, okay. This is N160, then thickness, this is in meter, then CSR 7.5, okay, and volumetric strain in percentage, then for M equal to 7.5, then volumetric strain percentage for any m, here m equal to 8 or mw equal to 8, and this is the delta H or the settlement in meter. Okay. So, these are the tables. Now, how I will calculate this CSR? You can say this is actually tau average by sigma V0. Now, what is that? This is CSR. CSR is equal to your tau average divided by sigma V0 dash, and this is valid for only 7.5. So, that is why it is written CSR 7.5, tau average divided by sigma V dash. So, here it is N116 is x direction, y direction is CSR, and this is volumetric strain in terms of percentage. This is 0.1, 0.2, 0.5, 1, 2, 3, 4, 5, 10. Clear? Now, how I will calculate the CSR? Because I should know the CSR and N160, then I will get the volumetric strain here. Okay. So, the CSR value I will calculate for 7.5 is 0.65 Amax by G into sigma V by sigma V dash or 0 into RD. Now, I will show you the calculation for layer 1, okay, layer 1 only. So, this is my layer 1, this is 2, this is 3 and this is 4. So, this for layer 1 CSR 7.5, that will be 0.65 Amax by V is 0.25, and for layer 1 sigma V is 19 because it is total, and sigma V dash will be 9. Again I am taking as the middle of the layer, so that is at 1 meter, and RD is will be equal to 1. You can see the same chart we can use, RD will be 1 here also. So, this value is 0.343. So, for the layer 1 N1, this is the your six is will be, this is 5, this is 5, this will be around 6, and this is 0.343 will be around here. So, this chart will be sorry. So, this is your, this is 5, this will be around 6. This is N1, 60 is equal to 6 for the layer 1, and this is 0.343 CSR 343. This is CSR. So, now if I draw it, so it will be this line. So, what is this volumetric strain? If I extend it, this is around 3.5. This volumetric strain will be around 3.5. So, this is 3.5%. So, now if I complete that table similar way that I did for the previous example problem, this is 6, thickness is 2 and it is 0.345. Now, for here for volumetric strain is 3.5 into this is 3.5, volumetric strain is 3.5%. Now, we have to multiply the correction factor for magnitude correction factor, that is again 8, that will be 1.125 again. So, if I multiply it 3.5 into 1.125, then I will get 3.94 in percentage. Then I will calculate the settlement, that is 3.94 into 2, divided by 100, because this in percentage, it will be 0.0788 in meter. So that is the settlement for the first layer or sub layer. Similarly, I will go for the second layer, where n is 60, 10, n1 60 is 10, this is 2, CSR I will get 0.343 at middle of the layer, that means 3 meter from the top, and this is 2.5. Volumetric strain is 2.5. If I multiply it, I will get 2.81. Okay, and settlement I will get 0.0563. So one more thing I want to mention, that the effect of two directional shaking, that you have to multiply the volumetric strain by 2, that is applicable for dry sand only. The saturated sand, such recommendation is not given. Okay, because saturated sand, that is the dry sand, so that recommendation is for the dry sand. Remember that. Okay, so for the 3, it is 8, it is 2, then 0.333 is the 3SR, you can calculate, it is 2.75, because it is 8. So that's why volumetric strain is also more. If I multiply the 1.125, I will get 3.1 percentage. And settlement will get 0.062 meter. For fourth layer, it is 8, fourth layer it is 12. So fourth layer it is 12, 2 is the thickness, it is 0.326. This is 2 percentage. Okay, it will be less because n value is high. So it is 2 percentage. So if I multiply it, I will get 2.25, and settlement will be 0.045 meter. So if I add them, I will get 0.242 in terms of meter, or 242 millimeter. Okay. So in terms of, so this is the saturated sand. You can see that settlement will be more compared to the whatever the soil parameter I have taken, compared to dry one and this one. So this is the settlement. So that is for saturated sand, we can calculate 242 millimeter. Okay, so this is the end of this settlement of sand part. Now I will discuss about that how I will go for the seismic or liquefaction hazard mitigation. So mostly I will discuss about the liquefaction hazard mitigation, but few mitigations can also be used for seismic hazard. Okay, so reduce the deformation, okay, or lateral spreading for liquefaction, or for settlement reduction also, those can be used for in combinedly seismic or liquefaction hazard mitigation. So the mostly I will go for the ground improvement techniques. So that means I will discuss about the ground improvement techniques to mitigate the seismic or liquefaction, mostly the liquefaction mitigation hazard, because liquefaction is the major problem in geotechnical earthquake engineering. So that means there are the four ways that can be done. First one is the densification, second one is the reinforcement, third one is the drainage, and fourth one is the solidification. Okay. So densification means we will densify the soil, okay, so that we can reduce the settlement, or we can reduce the amount of voids within the soil, or we will densify the soil so that we can reduce the settlement. Okay. And the second one will get the reinforcement, that means we will provide some reinforcement or stiffer material within the soil. So we will get the overall stiffness of the soil will increase. So our performance of the ground will be improved under seismic condition. And third one is the drainage. For example, you know the liquefaction, the cause of liquefaction is the generation of excess water pressure due to rapid loading under undrained condition, because the undrained condition. So, now if I provide a drainage path so that the induced excess water pressure can be dissipated through that drainage path, so that this water pressure will not generate, so the reduction of the strain will be less. Okay. So, that means we can provide a drainage path through that drainage path. If the water can dissipate, then that will reduce the possibility of liquefaction, can be reduced. And the fourth is the solidification, that means provide some material so that the pores of the soil can be filled by those. So, now this densification can be done is that vibro techniques, dynamic compaction, blasting and compaction grouting. Okay. So, one by one I will discuss all these techniques. The reinforcement can be done by stone columns or compaction piles. Drainage can be also done by stone column or PVD, prefabricated vertical drain, and solidification can be done by grouting and mixing. Okay. So, now first we will discuss about the densification technique. So, we have the 4 techniques. First we will talk about the densification techniques. It is one of the most common and useful techniques to mitigate the seismic hazards like liquefaction. It reduces the tendency to generate excess water pressure due to the cyclic loading, because the amount of voids is being reduced. So, the tendency positive excess water pressure due to liquefaction will reduce. Why? Because if we densify the soil, if it is a loose stage, it can go to the dense or moderately dense. So, that means when there will be the seismic loading, so that the dilatancy may occur. So, which reduces the generation of positive water pressure, because we know because of the dilatancy your water pressure is negative water pressure. So, that means if the tendency of generation of positive water pressure will be reduced, so strain reduction will also be reduced. Okay, so that is the idea. Settlement is produced due to densification. So, remember that because of the densification, a settlement will be occur on the surface. Now, displacement decreases, but acceleration may increase due to densification. But one more thing, that we will reduce the displacement, but as the density increases, the acceleration may increase due to densification. Okay. That can be done by vibro technique, dynamic compaction, blasting and compaction grouting. So, let us discuss about that techniques one by one. First, we will discuss about the vibro techniques. So, vibro techniques can be done in 2 ways. So, it is we are providing the vibration. So, one is based on the horizontal vibration or the lateral vibration we are providing. Another one we are providing the vertical vibration. So, if I provide the lateral vibration, then we can use the vibro flotation. So, that techniques is called vibro flotation, or that where we can provide the horizontal vibration. Another is vibro rod system, where we can provide the vertical vibration. So, first if I go for the vibro flotation, so it is most effective for clean granular soil, or amount of fine should be less than 20% or clay content should be less than 3%. So, it is most effective if it is a clean sand, or the amount of fines is less than 20% or clay content is less than 3%, then it is very effective. Very high density, around 100% relative density can be achieved within 30 to 46 centimeter around the vibro float. So, this we will use the technique is vibro flotation, and the instrument that we will use is the vibro float. So, that vibro float instrument will insert into the ground and then we will provide the vibration. So, around laterally around 30 to 46 centimeter of the soil can be achieved a 100% relative density. or 100% relative density can be achieved around 30 to 46 centimeter of the vibrow laterally, because here we are providing a horizontal vibration. Vibrow flotation is done in a grid pattern with spacing say 2 to 3 meter. So that means we are providing all these techniques in a grid pattern. Grid pattern means it is say this is one grid, so square grid if I provide, so this is a grid pattern. So with a say spacing between 2 to 3 meters. So with the spacing of these grids varies from 2 to 3 meter. Okay, so these grids, every point will apply insert that vibrow float and we will provide the vibration. Then again we will go for 2 to 3 meter apart, and then again we will do the same technique. Okay. So this technique has been successfully used to densify the soil up to 35 meter. Clear? Now vibrow rod system, where we can provide the vertical vibration. So vibrow rod system is effective for similar type of soils where vibrow flotation is most effective. So that means where vibrow flotation technique is most effective, the similar type of soil can be effective for the vibrow rod system, or vibrow rod system can be effective for those similar type of soil. But due to the vertical vibration, the radius zone of influence is usually smaller in case of vibrow rod system as compared to vibrow flotation. Clear? The grid spacing is less as compared to vibrow float. The vibrow float, the grid spacing was 2 to 3 meter, here it is less because radially this influence zone is much less compared to the vibrow flotation. So your grid spacing is also less as compared to vibrow flotation in case of vibrow rod system. Then third one is the blasting. This is loose granular sand, the silt content less than 20% and clay content less than 5% can be effectively compacted by blasting. So that means here underground blast, we have to do as underground blast to densify the soil. Okay. Now explosives are placed vertically within boreholes at a height difference of 3 to 6 meter. That means the height difference 3 to 6 meter, we have to provide the explosives to create the underground blast or blasting. Now boreholes are usually made with a spacing of 5 to 15 meters. So this is also under in grid. So these boreholes are made usually spacing of 5 to 15 meter. This grid spacing. 2 to 3 rounds of detonation are generally used. So that means first we do a first round of detonation with a spacing, with a certain spacing in the grid pattern. Then in the later round, the detonations are done the location in between the first round of detonation. So that means first we do the testing, and then we will check the how much densification is being done, and then based on that you have to go for second round or third round. So when you go for the first, you do the first round of detonation, then you will check how much densification is being done, then you go for the second round, and then second round the detonation will be done, the spacing in between the first round of detonation, and then you will, if required, you can go for third round of detonation also. Okay. 2 to 3 rounds. So blasting is commonly used to densify the completely saturated soil as effect of capillary tension or gas bubble reduces the effectiveness of blasting in partially saturated soil, though blasting is effective in dry soil. So that means the blasting either we have to do it for completely saturated or dry, because if it is partially saturated, then it is not that effective due to the presence of capillary tension or gas bubbles. Okay, so that means if it go for the saturated soil, due to blasting, localized temporary liquefaction helps the soil grains to move into a more dense state. Okay. Generally, we prefer it for the saturated soil, this technique, and due to the blasting, the localized temporary liquefaction helps the soil grains to move into a more dense state. Blasting is quite economical, but has limited use due to the possibility of damage of the nearby structure. And one more thing, then in the your dynamic compaction, that we can design it that in advance, that this is the influence zone I want to compact. What would be my weight? What would be my height of fall? So that we can design. But here the blasting, it is very difficult to predict the effectiveness of blasting in advance. So that's why you have to check it. First round of blasting you have to do it for 2 to 3 rounds, because first round you do it and check it what is the compaction or what is the performance of the blasting. Then you have to go for another round, and if required you have to go for one more round. Clear? And the last technique for this compaction is the compaction grouting. Okay. So, grout is injected into the soil under very high pressure. So, injected highly viscous grout forms bulbs or column which densify the surrounding soil by displacement. So, here a grout material is being injected into the soil very high pressure, and then this injected highly viscous grout, that they will form a column which is called the grout column, bulb or column into the soil. So, that will displace and then it will densify the surrounding soil. Clear? The grout point spacing is in the range of 1 to 4.6 meter. Here also it is done by grid pattern. The spacing is 1 to 4.6 meter. The deeper soil treatment, larger spacing is generally used. As this technique does not produce any vibration, it can be used in all type of soils, because in the vibration techniques, what we have discussed in previously, vibro compaction or the blasting, dynamic compaction or the vibro compaction, there the vibrations are produced, and here that's why if it is a clean sand condition, these techniques are very effective. If the fines are present, then these techniques are not that effective, although definitely some threshold values are there. So, beyond that fine content, it is not that much effective. Less than that, it is okay, and those things are given. But as this last technique of this compaction grouting, or the technique of compaction, which is compaction grouting, where it is not producing any vibration. So, it can be used for any type of soils. It is most commonly used in sand and non-plastic seals. It has been used to up to a depth of 30 meter. Okay. This technique is most effective for soft and weak soil also. Okay. The remediation of foundation settlement for shallow depths is another most common application of compaction grouting. So, we can provide the lifting of slabs or the remediation for foundation settlement for shallow foundation. It is another most common application of this compaction grouting. So, this is the part of this compaction technique. Now, there are 3 more techniques are there. One is drainage, another is your reinforcement, and then the last one is solidification. So, in my next lecture, I will discuss these other techniques also, okay, and then I will provide you some design charts for one particular technique, so that we can design that technique in the ground to mitigate the liquefaction hazard. Thank you.